Hello, welcome back to Statics. We're now on chapter 3. We are starting to look at these objects in their rigid body status. And we are trying to now figure out what should happen or how we can analyze a case where a rigid body has some force that is applied onto it, but that force does not only push or pull the rigid body, it tends to turn the rigid body. So we will be looking at forces, moments, and moments about an axis. Forces, moments, and moments of those forces about an axis. Right, so let's jump into chapter 3.1. Chapter 3.1 on forces and moments has got 6 key principles. 6 key principles. The first principle is on internal and external forces. The second principle, we discussed about it, transmissibility of forces. Transmissibility of forces. The third principle is two-dimensional vector products. So you have done several calculations, you have performed several calculations for vector products. We will just reintroduce the vector product calculation and identify or cite or locate its use in what we are trying to study, or its relevance in what we're trying to study. Then vector products in 3 dimensions and moments about a point and an axis. Right, so those 6 principles guide our calculations for this lecture. The first principle is that we will work with external forces that are acting on a body. An example of a body is the vehicle that is shown in figure 3.1, part A above there. That vehicle is a huge truck, and there are 3 people that are trying to pull this vehicle. Their pulling force can be described by some force vector F in the x direction. However, this truck is obviously a mass. The mass is made of many objects, so we can just approximate right now, right? We can just approximate, but with time, we will be able to calculate. The point at which the resultant of all those masses, right, have an effect due to the force of gravity. So there are several masses: the mass of the engine, there's a weight that is generated due to its mass, the mass of the tires, there's a weight generated due to those masses. So all those masses will result in the generation of a weight force, but the resultant of that weight is what we are approximating to be located at some point which we can call the center of gravity. So we are just approximating right now. We will calculate, but that's not the point of this discussion. So obviously we're just identifying forces that are acting on this object: the pulling force, the weight, and the reaction of the ground on this truck. So all these forces, as they act, when you look at these forces, these are all external. These are all forces that are generated by objects or fields that are outside the vehicle. The people that are pulling are outside the vehicle. They attach their cable and they generate a force. The weight is generated by what? By a vector field. So we've got a gravitational field that is generating the weight force on this truck, with a tendency to pull the truck towards the earth. Then from there, you'll obviously see that you've got the ground, because if we did not have the ground, then we would end up having a vehicle that is falling from wherever it is. This ground will generate a reaction force at each point of contact of this vehicle. So that's those forces R1 and R2. So this vehicle, this truck, is experiencing forces that are generated external from the object. If we are to look at, for example, some forces due to your tightening of the bolts and nuts, right? So obviously when you're tightening these bolts, you're generating some forces, right? There's some forces due to some object that is inside there that has got its own mass, and it is exerting a force due to its weight. There is another force that is holding the pieces together, right? So there is this section of the truck and that section of the truck. There are bolts that are obviously interconnecting the two. And these bolts or these members or these beams will obviously have to pull the front section to the back section. There is the chassis on which we have placed the back part of the truck. That chassis tends to hold itself together. It is made up of rails that are interconnected, and then it's connected to the wheels. For it to be intact, those rails must be pulled to each other. So there is something like a railway, right? So there are some other members or beams that interconnect the two rails of the chassis. So the whole idea is all those other forces are internal forces. We are not worried about them. So in this module and in this chapter, we are only concerned with external forces for chapters 4 and 5. We are just studying chapter 5, so we do not need to look at internal forces. Internal forces are for those that will use this textbook to study chapter 6 and 7. So this means that our point of focus, according to this first principle, is to look at the external forces that are acting on a body and the effects of those forces, which gives rise to what we want to discuss, called the moments of a force. The second principle, after the first principle on external forces, the second principle that we will use in this chapter is the principle of transmissibility. So I think we discussed that in the first meeting. So any two forces, F and F prime, acting on a body, generate the same effect as long as these two conditions are satisfied. Those forces should have the same magnitude and direction. Second condition, those forces should act along the same line of action. So the first example here shows the force F acting at a point A higher up on this object. Then there's another force F prime, which acts at a point B lower down the object. The line of action, or X, for these two forces is one and the same. The direction at which these forces are oriented relative to a common reference frame is the same. The magnitude of these forces is exactly the same. So these form equivalent forces. So because these are equivalent and these forces are acting along the same line of action, then they are equivalent. The effect of these two forces is one and the same. In other words, you can just slide a force on a rail called the line of action and make use of the principle of transmissibility for your convenience. There are certain things, though, that this principle of transmissibility does not address. So this second figure here, figure 3.4, shows how we can make use of the principle of transmissibility and the limitations of the principle of transmissibility. So in figure 3.4, part A, we see two forces P1 and P2. These forces have equal magnitudes, but they are pointing in different directions. So we see a set of equivalent forces, but these are acting in different directions. Now, the force P1 acts in the minus x direction, the force P2 in the positive x direction. By the principle of transmissibility, we can transfer force P2 along this line of action to a new location, from location B to location A, to end up having a diagram like this. So this diagram has the original force P1, but it now has the equivalent force of what? Of P2 acting at location A. We found it by simply transmitting or moving this force to that location A. Now when we sum up these forces, by virtue of these forces having the same magnitude, they add up to 0. So in the end, we have the object with a resultant force of 0 acting on it. So it is at static equilibrium. It's just seated like I'm done. Then, in the second case, we have those same forces anti-parallel. So if these forces are pointing at each other, once again, by the principle of transmissibility, we can move or slide force P2 along this line of action and locate it at what? At point B. So this is the equivalent force for P2 that is now acting at point what? At in fact, its point of action is what? Is the middle center, is the middle there. I'll just call it center C. So because of this, if we add up these two forces, once again, we will find that they add up to what? To 0. So that's the use of the principle of transmissibility. The limits of this principle are simply the fact that the fact that we have two forces that are acting on this object. Physically, there is a stretch of this object in this direction and a stretch of the object in that direction. So this object this object is under what? Is under tension, right? It's under tension, it's being extended. Then compression, the reverse is true. I think kids love to do this one, right? So it's being compressed. So if it's a rigid body, by definition, it is not prone to deformation, but practically deformation is inevitable. So you will notice that these objects will experience some change in their what? Some change in their dimensions by some delta x. For this one, it will extend by some what? By some delta x. So the extensions or the compressions due to these forces are what we are ignoring in this part of the module. So this is the idea with engineering. You start from what is called the ideal case. Even with science, we start from the ideal case when everything is fine. There is negligible friction. There is negligible air resistance. Everything is perfect. All you consider are ideal cases. Then we move slowly from the ideal case and build a more practical situation by throwing in more variables. So for now, we don't want to complicate things. That's why we will use the principle of transmissibility and will not consider internal forces. So the second principle on transmissibility will be freely used. The third principle in this section is the principle on vector products. So this principle, remember, we will make use of all these principles interchangeably, and we will also put them together. So we'll integrate the concepts. So it's important that as we go, you home in on one concept and give yourself an hour to make sure that all the corners are now understood. So vector products is something that we've done before. Vector products are common in your physics modules. So this section just reintroduces vector products. So a vector product obviously starts with the definition of the vectors whose product you want to find. In other words, how do we multiply two vectors? Which is why in this module we are saying we are studying vector products and what? And moments. The products are different. There's something called the cross product. There's something called the dot product or the scalar product. So in this section, on this part, all we are looking for is the vector product or the cross product. By definition, the cross product is simply a third vector that is generated by two vectors. The two vectors are coplanar, An example is shown here, vector Q and vector P. They lie in one plane. They are oriented and they are separated by some angle theta. The vector product is a third product that is generated and has two properties. It is at a right angle, or it is normal to the plane of the two vectors. And its magnitude is simply defined by the mathematical or algebraic product, right, of the magnitudes of the vectors multiplied by the what? By the sine of the angle in between. And that angle is the smaller angle. The third characteristic or technique that defines the vector product is the right-hand corkscrew rule. The right-hand corkscrew rule. So it simply defines the vector product as the vertical vector that is generated when you cross or when you multiply some vector in some initial direction into the direction of the second vector, right? So that's vector number one, and if you turn it towards the second vector, then through that angle theta, then you land on the second vector. So that's the definition or another property that you can use to define or to figure out your cross products. So we've used these, the magnetic force, I think you now know it inside out. So I'm so excited because you guys are smart at this and you've done it recently. Okay, so one other property that is described in figure 3.6 on vector products is that it doesn't matter where this Q is. As long as it is in this plane, it will form a new parallelogram whose area is the same as the previous one. And because of that, we will be able to come up with the same cross product. This is why in the caption there, the text says, the magnitude of the vector product V is equal to the area of the parallelogram formed by P and Q. If you change Q to Q prime, which is this new vector position, it forms a new what? It forms a new parallelogram. So if you put it to Q prime in such a way that the parallelogram changes shape, but P and the area are still the same, then the magnitude of V remains the same. So by definition, we've got some interesting equations here. The product of the vector is given by P cross Q. So we can write this as the non-typed version of your vector products, which is P cross Q. And the magnitude, we have defined it already. Remember that the angle is the smaller angle. Remember that the angle is the smaller angle between the two. Then we have certain properties of these vector products. We have certain properties of these vector products. So this first property has been given when we find a new vector, Q prime, and that Q prime is selected carefully in such a way that the area is the same as the first of the parallelogram, is the same as the first parallelogram. You will still get the same what? The same cross product. Then property number 2 is that when we cross multiply vectors, the cross multiplication is non-commutative. In other words, Q cross P is not the same as P cross Q. Q cross P is not the same as P cross Q. In actual fact, what happens is this. If you have P cross Q, let's use the vector notation. So this is our P vector into our what? Our Q vector. If you have P cross Q, then you generate what? The cross product V. If you then think of it in the other way, do you notice that you're now forced to rotate? You're now forced to rotate your what? Your like into a boo, right? So if you're now doing Q cross P, you are forced to boo this vector, and therefore you're generating a negative sense of the cross product. In other words, if we have P cross Q forming a cross product in the positive vertical sense, then the reverse is true. We should produce a minus V there. For this reason, there is this rule that says your Q cross P should be the same as the negative of what? Of P cross Q. So that is the definition of the inverted cross product. The third product is an exciting one, distributive. So it's just like your algebra. It's just like A into B plus C. You can simply distribute this to AB plus AC. So this is exactly what's happening here. No need to explain that. Then P cross Q and then cross S is not the same as P cross Q cross S. So basically this one is one cross product, right? So if you have P cross Q and then we introduce a third vector, then if we have a third vector, then we are not going to necessarily get the same, in fact we will not get the same cross product as in the second. So this is a non-associative property. This is a non-associative property of the vector cross product. Right. When we are in three dimensions now, we need to think about these cross products in terms of their unit vectors. So just a quick reminder, our unit vector in the x direction is I, our unit vector in the y direction is j, in the z direction is what? Is k. So the cross product is actually defined by these unit vectors. If we cross I cross j, we will form a what? A k. So that is the definition of what? Of the third axis, the z axis. Now let's do it the other way. Let's cross j cross I. So I have to twist my hand, guys. I'll need momentum health to take me to hospital. So okay, I guess you get the point. It's one and the same thing like we said the other time. We would have to point this finger on the other side in order for me to rotate in the opposite direction. So because of that, my cross product becomes the opposite vector, or the negative vector. So this text is just emphasizing that the vector product of the I and j unit vectors is the k unit vector. In part B, which is this case, the vector product of the j and I is the minus k. So now in order for us to easily remember this, the textbook has got a cool method. So this method is foolproof. You won't have problems with this. So this method simply tells you that for you to figure out I cross j equals what, j cross minus k equals what, just write your vectors in the following format. So write your vectors in the anti-clockwise or anti-clockwise format. Your I first, your j second, your k third, in that format. When you have drawn or when you've written your vectors in that format, then for you to figure out the cross product relation, the positive sense is defined by the anti-clockwise direction. In other words, I cross something in its positive sense, j should give you a positive k, right? The same applies. Your j cross something in its positive sense, or the vector unit vector in its positive sense, k should give you a positive I. The same applies. Your k cross I should give you a positive j. So let's just see the summary table that explains that. So the summary table is here to tell us that our I cross j gives us a k. Then we said our j cross k give us an I. Our k cross I give us a j. Now let's operate this the same way but in the reverse direction. So let's think about it in the reverse direction. how you can determine the unit vector for the product when you are given some vector in 3 dimensions. Now let's start with I cross k. I cross k. I cross k is obviously going to give us a what? A j. But since we are in the clockwise direction, then instead of a positive j, we will get a negative j. This is why our I cross k give us a negative j. The same applies if we now say k cross j. K cross j will give us a what? A negative I. K cross j will give us a negative I. How about j cross I? J cross I will give us a negative k. So all these are just straightforward methods of remembering how to figure out the cross product in 3 dimensions. Okay. The important ones, I think you already know this. The cross product is still the same thing. As long as these are vectors. If we are saying I cross j, all we are saying this is the size of I multiplied by the size of j multiplied by the sine of the angle between what? I and j. And we know that as long as we are talking I and j, or I and k, or j and k, the angle between them is what? Is 90, and sine 90 is always 1. But if we have this case where I cross I, the angle between them is 0. This is why all the vectors that are, if you cross product vectors that are collinear or coaxial, then their vector product is a 0. So this summarizes your vector products. You will notice then that for that calculation that we came across, this is the definition of your cross product. We had P, vector P, and vector Q. We said that our vector V is equal to what? Is equal to P cross Q. P cross Q. However, we know that the vector P is a P in the xi plus P in the yj plus P in the zk. I always forget these things. And then we want to multiply this by a Q in the xi plus a Q in the yj plus a Q in the zk. So if we then start to use the distributive property, you will notice that you can hold your px in the I and multiply by everything. However, the first product will obviously be equal to 0 because I cross I are equal to 0. What we are saying is this. P in the x is now multiplying everything, right? So we have P in the x multiplying this whole bracket. We have P in the x multiplied by Q in the x. The first unit vector for P is an I. The unit vector for Q is another I. Plus, that same P in the x is now multiplying what? Q in the y. The P in the x was in the I. The Q in the y is in the j. Plus, that same P in the x is multiplying Q in the z. The P in the x was in the I. The Q in the z was in the k. So, I cross I is what gives us a 0. I cross j, then we come straight to our circle. I cross j gives us a what? A k. So, this product is in the k direction. How about I cross k? I cross k is in the, I cross k is now in the negative j. So, because of that, you will come up with this solution that can be found by the determinant of this matrix. In other words, the determinant of this matrix is actually a result of a cross product calculation, right? So we can debate, physicists and mathematicians will debate and say, okay, the physicists came up with the vector product, and it can be used to actually derive this matrix determinant method. The mathematicians obviously say that they are the ones that started, so okay, the fight can continue. But otherwise, it's cool, right? So we are actually discovering that the cross product is actually what defines the vector method of finding the cross product using the matrix method. So in other words, your x components will start from the y, z minus zy. The y component will start from the zx and then minus xz, and the permutations are just like that. So that's the definition of the cross product. So in this slide, I've got a small suggestion. Remember in the first slide, I suggested that you play around on some project. So I gave you a small project to play around with. So I gave you an idea that you need to find some angle in 3 dimensions. So you can use a cardboard, you can use maybe a perspex glass, as long as it's flat and planar, and then you can find some unknown angle. Now, so you need just some string, right? You need some string. You tie it in some point, and then it lies in a certain orientation that is not fixed. So then you can find those angles and prove that concept. But this time now, we've got a new idea of a project. So this project is basically something that you can do on a game if you're playing some car game, or if you're playing some aircraft game or something like that. So as long as you can approach some object from behind, and then you knock it at an angle, right? Just like you would do a pit maneuver on your game. So this is what defines the moments of a force about some point. The moments of a force about some point. The reason why we were studying the fundamentals, which is the vector product, is so that we can figure out the moment of a force about a point. Now, the moment of a force about a point is something that we've studied already. It's a vector. It's a vector, and this is a product of what? Of 2 vectors, which are the position vector and the force that is acting at that particular position. The moment in itself physically is just a turning effect. That's why we say there are some external forces which when they act on a body. Remember, external forces will either lead to translation or rotation of some rigid body. So in this case, the forces that we're considering have a tendency to turn the object. What kind of an example can you think about? So there's several examples that you can think about for you to figure out moments of a force. When we look at the reaction on a table, right? Your table sits on the floor. It has 2 legs when you look at it from some elevation. If we were to remove one of these legs, right, its weight has a tendency of rotating it. Its weight has a tendency of what? Of rotating it. It has a clockwise moment about a what? About some point. Now, the reason why you put this other set of legs for this table is because you want to generate a counterclockwise moment, so that this table is at what? At equilibrium. So rotation and just the turning effect are not supposed to be confused. We are not talking rotating objects. We are discussing stationary objects that are in static equilibrium, but they are in static equilibrium because you have designed it in such a way that turning effects can cancel out. So there's someone who suggested, how about the turning effect? This is the module topic. This is the topic. So this is where we will make use of these principles to try and understand moments about a point. So by definition, we just said the moment is a turning effect. And this turning effect is calculated by finding the cross product of the position vector and the force at which acting at that position. So this diagram is showing those 3 constituents of the moment of a force, or the turning effect of a force. At first, we have some object. So this is our rigid body. On that rigid body exists some force that is acting on its plane, right? So on that rigid body, there is some plane that has been selected. This plane, I can just call it P. And that is the slice that you see there. So the force that is acting on this body is the force F. This force F is acting at some location, in this case, right at its circumference. So someone is tied. No, it's not a potato. Okay, so rigid body, by the way. Okay, potato is not really a rigid body. Maybe I'm hungry, guys. Okay, so someone is tied a string there, and we can find the position of the string relative to some origin. We have just decided, okay, let's call this point the origin, or 0, 0, 0 in 3 dimensions. The position at which that force is acting is the R. The position is the R. The R is a position vector. So you write it in its vector form. The point A is where we have the force F. The cross product of this position with the force is the moment. So in other words, we can now apply our rule. So the first vector in this calculation, the first vector is the position. So that's our R, and then the intention is to curve the R towards towards the force, is to turn the R towards the force. And you actually learn that the direction in which you want to turn the R towards the orientation or the direction of the force becomes the sense of rotation of the moment. Okay, so that's the definition of the moment. However, if you look at our diagram, there are certain things that we can relate to. This is a plane, right? This is a plane P. So on that plane, we have this force, we have this position vector R, which we can, by the principle of transmissibility, extend to that point with some equivalent vector R prime. Now that we have this arrangement, which we are used to, right? This moment can be thought of as a moment that is acting at that point. Now, when you look at this diagram, what we can tell is that the force can be related to this R. The force can be related to this R. How? We said that the moment is actually equal to an R cross the force F. We said the moment is an R cross the force F. And we said by magnitude, one can actually find the magnitude of this moment about the force by multiplying the magnitude of R multiplied by the force F and the angle between them, which is sine theta or sine theta. When you look at this diagram, however, there is something that resembles this theta. If you notice, there is something that resembles this theta. Do you notice that this theta is the same as this angle here? This theta is the same as this angle there. And if we are to look for the trig ratio sine theta using the triangle OAC, what we end up discovering is that sine theta is actually the ratio d to the magnitude R. For this reason, we can actually write our d as R sine theta. In other words, this equation can be rewritten as n F multiplied by R sine theta. This R sine theta is what we already found from this trig ratio on the other side. And we said it is the same as this distance d. For that reason, the moment about the point O is also defined as F times the d. And that d is a what? Is a perpendicular distance of the line of action of that force from the what? From the point of rotation. So for that reason, the moment MO is also defined as R F sine theta, which is the same as FD. So this D is the perpendicular distance. In other words, you don't have to struggle much. All you need to do is to find some perpendicular distance between the line of action of the force and the what? And the point of concern of rotation. Okay, so if we have an equivalent force F equal to F prime, then it generates an equivalent moment. This topic actually points out that important concept, equivalent forces and equivalent moments. We are going to later on look at couples. Well, all we want to figure out is from a system that has many forces that are acting on it, which is reality, right? There are many forces that are acting on objects that we usually use, right? So, if there are many forces, how can we find the equivalent of those forces so that we can solve some problems? I gave an example last time, and it's actually very interesting and it's applicable still. That if you've got some crane outside there and it's hoisting or it's carrying some objects using some boom into some flat, so that crane is supposed to topple. If you look at all the forces acting, there is the object there that you want to that you want to place onto the flat. It's got some weight, right? The crane is at the road, and this boom is into the building. So there's supposed to be a weight that rotates this crane. All you want is to now figure out, okay, since we have this weight and this crane has got its own mass, there's a reaction from the ground, the boom has got it's got some strings or it's got some hydraulic system that is either pulling or pushing this object, then how do we find an equivalent force system so that we just counteract that? If we just find one equivalent force and we counteract it, the system is It's in equilibrium. Then our crane won't topple. So that's the idea. Our crane won't topple. So the curl is also defined here so that you can see that it can be applied to find the moment. So in the end, you want something that is equivalent. In other words, we can find an equivalent moment by applying a different force. This equation is telling us two things. The moment is equal to the product of the force and the perpendicular distance. This moment is the same. So you can choose to either raise the force if you have got energy, right? If you've eaten a lot of food, right? You can use all your energy at a very small distance, right? So you can raise the force and apply it at a very small distance. So you can think about it as this person here. They want to fasten or to lock a nut, right? So you've got your what are these? There's a proper name for this tool, right? There's a proper name for this tool. So it is a shifting spanner, if I'm not mistaken. Right? I call it a shifting spanner from the exposure that I got with some guys that I was working with at some engineering company. So if you've got some other term that is actually technical, please help me so that I use the right terms. Right, so this is shifting in the sense that it's a spanner. It will lock to there's a hexagonal shape of those bolts and nuts. So it will lock to those. You can then shift it to fit onto different sizes, even though it's not really the right way to do things. And then you can use it as a normal spanner for different sized nuts. So you've got this spanner, so it's supposed to unlock a nut. So this person decides to use this spanner. Look at the distance. So they are applying some force here, right? They're applying some force. Let's say they are tightening. So it needs to turn clockwise if it is right hand threaded. So it needs to turn clockwise. They need to apply some force downward. And the force that they are applying is at a perpendicular distance. Let's call that D in that orientation. However, look at this person. This person here now decides, okay, instead of me struggling and applying a very large force, of course these are different cases, but let's assume that is the same nut that we want to unfasten or fasten. So instead of us using a D knot, which is this small, right? We want to generate the same moment. So if we want to generate the same moment, it's either we use D naught, which is small, D small, multiplied by F large. Okay, so you use a lot of force on a very small distance. Or this person decides, okay, why should I struggle? All I want is that same turning effect. So why don't I use a D, which is which is large, and an F, which is small. So they apply a very tiny force somewhere there. Let's say that's where they are. Let's call it force 2. Let's call this force 1, where force 2 is less than force 1. Then they apply a very small force, but over a long d, over a long distance between those two. So I'm trying to look for a color that will stand out. Yeah, maybe something like that. So that's the what? That's the d. So d2, let's say d2 is greater than what? d1. So they use a large d and a small force and do the same, manage to generate the same turning effect. So that is mechanics, which you can use now to do less work and achieve the same thing. So the moments are defined according to what is seen on figure 3.12. It simply says that a moment that tends to produce a counterclockwise rotation is positive. So that is the definition of the sense of a moment. If you've got a reference frame, so make sure that your moments which are in the anti-clockwise direction are actually positive moments. So let's say anti-clockwise is equal to positive, and then your clockwise moments are equal to negative. It depends with the axis. We are not saying plus k or minus k. It can be in any other axis. All you know is that whatever axis that you're considering, then if it's about that axis in the clockwise direction, then it's a negative moment. So that's the principle on moments. So we now have a definition of moments, and we will jump on to Varinon's theorem. So 3D components of moments is the next principle. 3D components of moments is the next principle, and it will summarize this section. So in figure 3.13, we have a situation or a case that is brought to us. This case is the reason why we need to apply the theorem defined by Varinon. So this is a situation where we have some point at which several forces are acting. F1, F2, F3, and F4. Remember, this can be a point on a rigid body. Now, this point is located a position R from some origin O of a rectangular system of coordinates. Now, Varinon's theorem states that the moment about this point, M about O, is simply a resultant. It's simply a resultant of these four forces, right? These four forces. So we are looking at the resultant of these four forces equals the sum of the moments about point O of the individual forces. If we find the individual moment about O due to force 1 and add it to the individual moment about O due to force 2, due to force 3, and so forth, if we add them up, we will get the same turning effect as that of the resultant. Do you notice that this is mathematically simplified here? It simply says that the moment, which is defined MO, is equal to your R cross F. So R cross F is in this case equal to the R cross many F's. The R cross many F's. And we are simply using the distributive property of vector cross products to then come up with this product is simply the same as R cross F1 plus R cross F2, and so on and so forth. Since we know that the vector R is in 3 dimensions, so it's a distance x in the I, y in the j, z in the k, according to equation 3.15. And the force F is an F in the x, I, F in the y, j, F in the z, k, according to 3.16. Then the moment can be defined according to those separate components. Hence the title 3D components of moments. So in other words, this principle simply is Varinon's principle. Principle number 6 in this study is Varinon's principle. If you are given a lot of forces that are acting on a rigid body, for you to find the moment of those forces, simply find the moment of the individual forces about the point of action. Right, so figure 3.14 emphasizes that each force, remember, is in the ijk, right? Each force, remember, is in the ijk. That is what we saw in that other equation. This means that your moment will be made of three components. Your moment will be having the I component, the j component, and the k component. Remember, the moment is a what? The moment is a cross product, so it's a vector. And in the previous part, we actually had a vector that is generated by P and Q. And we could see that it actually has x, y, and z components. So by the same sign, you've seen that method. So if you go to your table, your reference tables, there is a suggestion that you can use a matrix calculator. There's an online matrix calculator. So you can just try that matrix calculator out. It will easily show you how you can find these moments. Why? Because we are not here to test how you actually construct the matrix determinant. All we want to see you is applying it. So in this module, the interest is you should be able to write the matrix format, which says the moment is basically the first vector cross our second vector, and in this case these will be many forces, so we can actually say these are that's the resultant. So in this case we will simply have the I, j, and k components, which are now being used to find the determinant of your r in the x, or sometimes simply written as what? As x, and then your y, and then your z. This becomes your total f in the x, your total f in the y, your total f in the z, so that the moment has components in the x, y, and z. So you can actually find the x component of the moment, the y component of the moment, and so on and so forth. That defines your 3D components of moments. So from now, that moment that you learned at FVV 101, that was simply a moment in 2 dimensions. Let's now graduate and think about that moment in 3 dimensions. It's actually a turning effect, in this case, on a rigid body. And remember, reference points are defined by you. You are the engineer, you are the scientist. You need to figure that out. What reference frame should I use? So that I can then tell which is x, which is y, which is z, and so on and so forth. Okay, so 3-dimensional moments of components of moments can also be analyzed when we have moments that are not about the origin. So the origin is just our way of making life easy. But however, we notice that moments or forces that are acting on objects are not necessarily going to act on an object that is starting at an origin or at 0, 0. And we define that origin. So we might as well just have an idea of these moments if the forces are acting at any point, and we choose any other point as the reference point. So this is the same concept of 3D components of moments. But what we are looking at now are 3D components of moments when those moments are calculated about a point with reference to some other point that is not the origin. So in figure 3.15, we are given the case. So it is introduced to us in the form of that force that is acting at a point A. So the force that is acting at a point A, it has its components in the I, in the J, and in the K. That force is at a position RA relative to B. RA relative to B. Now by definition, when we write this position vector, RA relative to B, take note, you are going to use this concept in dynamics. And you will actually use it in other modules, I think. I just remember dynamics will need this. So when you write the vector RA relative to B, all we are defining is the position vector R at position A minus R at position B. That is the definition of the position vector relative to some other point. So you will notice that your x in the A relative to B, which is the x component of this vector will simply be your x at A minus x at B, the y the same, the z the same. Why are we doing this? Because we will not necessarily be given the origin as the first location about which we want to find some moment. So there we have it. We've got our force acting at that point. We've got the vector Ra relative to what? To B. And we've got the directions x A minus xb in the I to define the vector Rab in the I direction. And then we also have this in the J and that in the K. In other words, from point B to point A, you need to move in the x direction, a magnitude xa minus xb. You need to move in the J direction, a magnitude ya minus yb. You need to move in the z direction, a magnitude za minus zb. So the moment about the point B by a what? Of a force F applied at the point A is the vector product of the position vector Rab and force F. So we're just redefining the moment, this time not relative to the what? To the origin. So our moment about some arbitrary point B is given by the position at which that force is acting, which is A, relative to that point B, hence the vector Ab, cross the force F. So we've got our Ra minus Rb cross F, and we can just plant all these vectors into our matrix to determine the determinant, and then in the end we can find the moment about B. And when we have the moment about B, we actually have the components of the moment about B. Right, this is the two-dimensional problem, and you've done it before. So in a two-dimensional problem, you always had your moments now in the what? In the K, if it were 2 dimensions, just because you've got your position vector in the X and in the Y. Right, so your moment, let's say the moment is in the Z, it would be in this outside the page, for example, and then you've got the magnitude of the moment defined. All this is found from what? It's found from here if it's in 3 dimensions. Okay, even in 2 dimensions, you can use a matrix. I think you also know that you can use 2x2 matrices. So figure 3.17 is basically just a 2-dimensional problem. The moment MB about a point of a force. So this one is good because it's actually the 2-dimensional simplified version. In other words, if you want to find the moment about the origin, look at figure 3.16, study what it means. If you want to find the moment about B, which is an arbitrary point somewhere, then look at figure 3.17, and it will show you that in a 2-dimensional problem, the moment about B requires you to find the vector Ra relative to B. So that sums up the moments and their components in 3 dimensions. So there comes a sample problem 3.1. So this sample problem says a 100-pound vertical force is applied to the end of a lever. So free body diagram is here with us. The moment we see this, okay, I hope that we have, okay, you mentioned that you did your engineering drawing. So there is this line that you always see on objects. Even though there's a fat side or a thicker side and a thin side on the other side, this line always is drawn on the axis of whatever object of concern. So I hope you still remember that it is called the what? The axis or the datum. So the drawing is always such that the forces act on the datum. If it is a weight, it should act on the datum. If it is another force like this one, it should act on the datum at whatever position. So just as an aside. So the vertical force is a 100 pound. It is applied at the end of a lever. Then it is, which is attached to a shaft at O. So there is a shaft at O. This is the lever OA, and then we've got a force 100 pound at point A. Now we want to determine the moment of the 100-pound force about the point O. That's the first part of the question. So free body diagram, we've got our reference point, We've got our reference frame, x and y, so that's the first important part. Then we need dimensions, so let's draw the object. So the object in this case, we cannot just draw a point. We cannot draw a point. We're now talking rigid bodies. So on that rigid body, while it has its own weight somewhere, what we have is some force that we've been given at point A, and that force is acting in the vertical downward direction. So that's our force. Let's just call it F is equal to 100 pounds in the minus J direction. That's our force F. So we are what? We are annotating our free body diagram. That's a line that is a reference line. This line here is the datum, right? This line here is the datum. We are given some length, so let's just call that L is equal to 24 inches. That is our L. Then we are given some angle. The angle, let's call it theta, is equal to 60 degrees. Now we have a free body diagram of the case, which has a reference frame. It's got the forces acting, and all the dimensions are shown. There is this dimension which is just labeled D. It is not shown as far as its magnitude is concerned. So if we want to find part A, so you can supply, or maybe I can even write the data here. Our data as follows. Then you've got your F1, sorry, just the F, right? F is equal to 100 pounds. We said that is in the J direction. We said theta is equal to 60 degrees. We said what L is equal to 24 inches. That's our data. If we want to find the moment of the 100-pound force about O, so to find the moment about O of the 100 force, our equation, we know that we've got the sketch, we've got the data. We can now think about the equation. So the equation for the moment in general is either R cross F or FD. R cross F or FD. Which is more convenient in this case? We know that our R in this case, our R is from where? From the point of rotation to the location of the force. So in other words, it's A relative to O, or the distance or the vector in the OA direction, right? So you can write it as A relative to O, or the distance in the OA direction. Now, if we want to find the moment about O, then it means that the vector direction, the sense of the vector direction, we said our R is up there. Look at what I've already done. I've had to rotate my hand. Our R is up there, and the force is downward. So my R, for it to end up lining up with the force, it will have to be rotated in the what? In the anti-clockwise. So I already know the sense of rotation of this vector according to the reference frame, and we have a z direction. We're now in 3D. Then this moment must be in the what? It must be in the negative k direction. So let's use the two methods. Then the rest of the parts, I think you can do them. So let's use the first method, R cross F. Then we'll use the second method, FD. So M being equal to R cross F. Remember, for the FD, I've had to what? To append the sense, because these are magnitudes. So R cross F. What is my R of A relative to B? What is my R of A relative to B? So this is my what? This is my R vector. A relative to B, it's this horizontal component plus that vertical component. So let's use our minds. We are used to this now, so I will just say it's an L cos theta in the I plus an L sine theta in the J. Right? This is the R. Cross or multiplied by our F in the what? In the J, in the minus J. So basically, in symbols, we can now enjoy ourselves and write our L cos theta multiplied by F. And then the vectors that will multiply are I cross a negative J. plus the second one, L sine theta. Need we continue with this one? No, because it's just F. Then we multiply with what? With a J cross a negative J. J cross a negative J. I want to put a proper vector here. So let me just do that. And then let me just do that. Okay, fine. So this one, we know that it tends to 0. So our first part is the solution. Our first part is therefore L cos theta multiplied by the magnitude of the force F. What is I cross minus J? What is I cross minus J? So we come to our system of interpreting the I, J, K components of a force. What do we want? I cross J. If I cross J and if both are positive, we should get a positive K. So which means this negative is what will create a negative K. So this now means we've got an L cos theta multiplied by the F, and the sense has been derived from vector product calculations. Now, look at what is happening here. They gave us this dimension. Do you notice that this dimension, D, is actually the what? The perpendicular distance. So let's use the principle of transmissibility. Let's generate another force that is equivalent to the first one and locate it there. So that's our F, but it's an F prime. Do you notice that about the point O, this force F prime will generate the same effect, a perpendicular distance D from the point O. For this reason, you will notice that from our trigonometry, this D is actually the horizontal component of our what? Of our R. In other words, it's actually L cos theta, which is the same as D, because D is this part. So it's actually D multiplied by what? By F. So we now have our FD after all. So in fact, I was saying we're going to do two methods. We have already done the two methods in one. So that's our DF, and it's in the minus K. So the moment is just the distance D multiplied by F. So you can do the math and you can prove. The second part of this question then asks, determine the horizontal force applied at point A, which creates the same moment about O. The horizontal force applied at point A, which creates the same moment about O. So we are applying a horizontal force at this point, and we are removing this. What we are taking from this F is the moment that it had created. So we now have, let's call it P, the horizontal force. So if you have a horizontal force, this is now part B. The horizontal force, by definition, we have our moment about O being equal to our R cross F. Now that we've already seen how we can determine the D, why don't we just use the what? Let me just do that. Why don't we just use the D of our new force P multiplied by F? And then the sense we know that what's happening is we've got the R, right, the original R cross the force. So if the force is in this direction, it will generate the same sense of the moment. So it's in the minus K. So I can still append minus K or force it. What is the perpendicular distance? So let's just generate the perpendicular distance from this point of rotation. So we will need obviously some vertical line up to that point. And by the principle of transmissibility, if this force P has an equivalent force that is acting at that point P prime, it will generate, that's a right angle, it will generate, so this is our dP, this is our dP. It will generate a what? A moment, which we can calculate. And we've been told that it is supposed to generate the same moment. So if it's supposed to generate the same moment, in other words, we're just taking the answer from this part. So let me just write the answer as what? Let's just call this moment for the first calculation, moment 1. So moment 1, whatever value that you got, should now be equal to what? dP. How do we find dP? If you use your trig, look at your free body diagram. So this is our dP. So you will notice that it is basically the vertical what? the vertical component of this length. So that's L sine theta. So that will be your L sine theta, that is, sine theta, that is dP for the force P. And then you multiply that by the force. So that force, that force is P. That force is P. So this is the force P, and this is the force P. Okay, so now you want to find that force because you already know the moment that it must generate. So your force P must now be equal to your moment, M1, whatever value you got, you divide that by sine theta, and you've got whatever value that you get. So this is just an example of making use of your moment definitions. Just look for that perpendicular distance to make life easy for yourself. That summarizes the first section 3.1 on forces that are generating a turning effect. So we were introduced to the vector product. We started from the principle of transmissibility so that we can make use of it, and we're working with external forces. And then we moved on to use the vector product, look at its properties, and use it to find the moment about a point. So in 3 dimensions, you can now find a moment about some point. So this is your chance to have fun. This is time to do some experiment. You want to generate a turning effect, right? So you just place some object. Usually beams are easy to use. But what you want is to tie a rope on the beam and create a pulling effect, right? You want to create a pulling effect at an angle that is not on the table, right? Because on the table, that's our usual XY axis. So you can't tell what's happening. So you want this pulling effect to be at an angle. That's the 3-dimensional case for you to calculate moments about some point. How about situations where this object that we had, for example, where was it? This one. How about a situation where this force is continuously leading to rotation about some axis? So this will be some vertical axis. Let's call it, I don't know, some axis OL, right? So it will generate some rotation about an axis. How can we actually use the math to find the moment about an axis? Because rotation is either about a point or about an axis. That is what happens with all forms of rotation. You either rotate about a point, So if I'm rotating this pen about a point, I will hold its point or whatever point I wish it to rotate about, and I will apply a force elsewhere, and it rotates about a point. But I can make it rotate about about an axis that is at its center. So if I do that, it begins to rotate about an axis through its center. So moments about an axis are now requiring us to look for another type of a vector product. For another type of product of vectors, right? In this case, it's called a scalar or a scalar product. So the 3 principles in this section are scalar products, mixed tuple products, and moments about an axis. Scalar products, mixed tuple products, and moments about an axis. So this section simply introduces the first part, which are scalar products. You have done this before. So figure 3.18 is an example of 2 vectors P and Q, and this principle simply states that there is an angle theta between those 2, and you can define the scalar product using that equation, which simply says P dot Q is, so your P vector dot Q, that's the dot product, it's simply equal to the magnitudes PQ multiplied by the cosine of the angle between them. With the vector product, we were calculating we're using the sine, this time we're using the cosine. Commutativity, dot products of 2 vectors are commutative. So P dot Q is the same as Q dot P. Because you're finding a number, you're finding a dimension. Okay, it can have dimensions, but you're finding a non-directional quantity. Yes, it's just a scalar. So these will be the 2 vectors, your vector Q and your vector P, and the angle between the 2 vectors. if you find their magnitudes, if you find this length or this, if it's a force, you find its magnitude, the same applies, you find for the other one, and you multiply those two magnitudes, you multiply them, and you multiply them by the cosine of the angle between them, you get the vector product. And it is not a vector. The product of those two is a scalar. It is also distributive, so it's the same as what we saw with vector products. They are distributive. So P dot Q1 plus Q2 will give you P dot Q1 plus P dot Q2. So in this part, we are just reminded that if we are using a cosine between the two vectors, right? Cosine between the two vectors. It's obvious that if they're at right angles, then they're at 90 degrees and our cosine becomes 0. So any vectors that are not in the same orientation will give you a dot product which is 0. If they're in the same orientation, they give you a dot product which is unity. And this is for unit vectors. So if we want to express the vector P now in its ijk format and the vector Q in its ijk format, you will notice that distributive property states that the px in the I is supposed to first multiply the qx in the I plus the qy in the j plus the qz in the k plus the p in the y the same, right? When you look at the first one, you will notice that the I dot I only takes place for components that are in the same direction. Everything else is crossing with another component at 90 degrees, leading it to a dot product of 0. So this is why your dot product is simply the sum px qx plus py qy plus pz qz. And you're done with your vector products. So the 3D scalar products can be used to find projections. You have done this before, finding projection of an angle, of a vector onto some other axis. So here we have some vector P. I think you know this already. That if there is some axis, in this case now we are not using the X or the Y or the Z. So we're just using some arbitrary axis or L. If we want to find the projection of the vector P onto the axis OL, all we need to do is to construct a right-angled triangle, where cos theta is simply given by the projection of P on OL divided by the hypotenuse, which is the vector P. So for this reason, we have the definition of the projection of the vector. So this equation, we have it from before. It can give us the what? Give us the angle. We can actually find the angle between two vectors using the dot product. On the right hand side, though, we are now defining the projection. I think we used this equation already. So this is basically telling us the projection OL can be found by simply finding the P cos theta. So since we already know that P dot Q is simply equal to PQ cos theta, do you notice that if we draw our vectors, right, maybe let me do it this way. If we draw our vectors in this way, where we have the P, and then we have the axis on which we are projecting it, right? And on that axis, another vector exists, which is vector Q. Your P dot Q still remains as PQ cos what? Cos theta. But you already know that P cos theta is the projection of P onto what? Onto the line or the vector OL or the axis OL. So this means that the P cos theta can be replaced by POL. So this is the meaning of equation 3.32. And if you now want to relate the direction, so you can actually find the projection of a vector onto another arbitrary axis. If you know instead of Q, you know a lambda. So the projection POL onto the axis OL is simply the vector P multiplied by the directional vector lambda. And I think you still remember our directional vector lambda. It's simply equal to the distance from whatever point. So let's call it OL, the vector, divided by the magnitude of that vector. So that's how we get our lambda. So this is an example of using the scalar product. You can use the scalar product to find the angle between two vectors. So this question says, 3 cables are used to support a container as shown. Determine the angle formed by cables AC and AD. So cable AC is there, cable AD is there. So this would be, we want to find the angle formed by the two. Right. So if we want to find the angle between the two, then you can now use your vector scalar, the scalar product of two vectors. I'm sorry, I keep saying vector product of two vectors. It's a scalar product of two vectors. Which vectors can we use? We can just use distance, position vectors, right? Position of D relative to A gives us a vector which we usually denote AD, right? If we create a dot product of that vector with what? With AC, all we have is the magnitude AD multiplied by AC multiplied by the cosine of the angle between them. This is cool because it's a pain to start to figure out. Look at this diagram. It's a pain to start to figure out because it's in three dimensions. How can you find this angle which is neither here nor there as far as our axis that we're used to is concerned, right? Because this position, look at this A here. Let's move from A to B, A to C, so that you can see where we are. This point is we want to move to what? We want to move to C, from A to C. In the x direction, we need to move. In the x direction, we need to move what distance? In the x direction, we need to move. This is the point C. So we need to move from this point A. Let's see. See, I'm already suffering. I need a distance which is like this. So in other words, let's see. Okay, we are on the y-axis. Perfect. That's fine. We are located on the y-axis. I see that dot here is actually on the y-axis. So we are already on the axis. So that's fine. But we need to move up and then to the right so that we can get located at that point from A up to what? Up to C. So let's just see, they are used to support this. I just want to be sure about the geometry here. If point A is indeed on the y-axis, from this diagram, it is on the y-axis. So, okay, so AC will not be a problem. It will simply be the vector AO plus the vector OC. So AC won't be trouble. But we want the angle between that AC and this other troublesome vector, which is AD. AD, for you to get to point D, you need to move vertically in the J. Then you need to move in the Z-axis up to that point, 360 millimeters. Then you need to move in the X-axis, negative X-axis, by 500 millimeters. So it now for you to say you want to find the angle between them, you want to create a plane. So it's rather use the math. So this is the math. It simply says that if you know how to come up with these vectors AD and AC by just following the points on the geometry, then you can find the angle between them because you have the geometry given there, and then you have the dimensions or the size. You can just find your square root of the x component, y component, and z component individually squared. Then in the end, you can make your cos theta the subject of the formula. So basically, I think there you will be happy to know that you can easily find the angle even if these objects are in space using the scalar product. So this example, okay, if you have got some time, you can actually finish it up. I just put some more space. Right, so mixed triple products are the second from last section. These products are basically defining what we will need to make use of when we are finding the okay, so we had found the moments about a point. Now we want to find moments about an axis. So this is where we use something called a mixed triple product. It's mixed in the sense that we have a dot product and a cross product. It's triple in the sense that we have three vectors. So by definition from figure 3.20, the mixed triple product is equal to the magnitude of the cross product of two vectors multiplied by the projection of the third vector onto the cross product. Let's be very careful with that terminology. So the mixed triple product is the what? Is the magnitude of the cross product. So it's a magnitude. It is a dot product. That's why we are discussing it as a dot product. It's a magnitude of the cross product of two vectors multiplied, so the cross product of P and Q. So this is the cross product of P and Q. Then it is multiplied by the projection of the third vector onto that cross product. The projection of S onto, let's call it OL. OL. So you are just multiplying this S by the cross product of the two. This is why it ends up just a what? Just a number. So for convention purposes, you can then list your vectors in this way. Your vectors that are forming the cross product, which are P cross Q, are in that direction, and then your S is the third vector. And the good thing is that your mixed triple products, they look the same like what we had for the I, J, and K. So this is the reason why in equation 37, the mixed triple product is defined as follows. S dot P cross Q. S, right, dot P cross, dot P cross Q in this direction is the same as P dot Q cross S, right? And it is the same as Q dot S cross P. So that's our cycle for the mixed triple product. So these are just denoting the negative sense. In other words, now the mixed triple product is simply a vector product between the third vector and the cross product V, which is equal to P cross Q. So we've just replaced this P cross Q by this V. And we know that the cross product is simply what? The sum of the product of the individual x-axis products, y-axis component products, z-axis component products. Now your mixed triple products, therefore, by the same sign can be found from this matrix calculation. However, look at what is happening now. Instead of us having I, J, and K, we now have S in the X, S in the Y, S in the Z. This means in the end you will have a scalar quantity. Because this is a vector, that is one vector, then it will form a scalar quantity. So in the end, as you can see here, these are just your magnitudes. So the mixed triple product actually defines the volume of this parallelogram prism, or parallelepiped, or the prism formed by what? By parallelogram. So we've got our two forces that created the what? The cross product V. Then those forces are now combined with a third force S, which will be projected onto the what? Onto O, let's call it OA. I'm trying to run away from L. So OA axis. So we are looking at the projection of this S on what? On OA, and then we find the mixed triple product. Hence this, so you can actually find the volume of a prism from that mixed triple product. This equation was defined already. So this example is basically giving you a chance to stretch yourself, determine the volume of the parallelepiped of figure 3.20b when P is that and that and that. So this is that figure because it started off like, okay, yeah. So if you look at your text, I think it's this one. It's this one, which is it's the one which with the parallelepiped, right? So all we want is to find the mixed triple product. So if you want to find the volume, which we can just define as the volume of that parallelly piped, so we've got the mixed triple product vector notation. So this is where you just extract that equation, your S dot P cross Q, S dot P cross Q. And then you can substitute. Your S is already given, 7I plus J minus K. Your P cross Q is a product that you can calculate from previous principles. The P is a 4I minus 3J plus 2K. The Q is a minus 2I minus 5J plus K. You use your matrix, you find a vector, you dot product it with S, and you are good to find a scalar value in what? In cubic units. Okay, so that is an example for the mixed triple product. Now, let's apply the mixed triple product to find the moment about some axis. So that's why we are at moments about an axis. So I'm concluding now. Please be patient. So moments about an axis through O are defined by the mixed triple product. The mixed triple product is given in this equation. It is simply the moment about OL being the axis, being given by the mixed triple product lambda, which is the directional vector of the axis OL, dot the moment about O. The moment about O is given by the R cross F. So in other words, pictorially, if we want to analyze this equation, we can just look at this figure 3.22. So in the figure, we have the point O, which is the origin. We've got our X, Y, and Z axes. We have some position vector R for a point at which some force F is what is acting. We also have the OL axis. So that is the axis that we want to determine a rotation about. So how do we do that? We need to find the directional vector of the axis. So it's actually simplifying the mixed triple product is simplifying life for us. This is how we can calculate a moment about what? An axis. So if we've been asked about the axis, all we want is to find what is the directional vector of the axis. That's the first thing. When you know the directional vector of the axis, then you can now consider the forces that you've been given. If it's an F, at what point of the rigid body is it acting relative to the what? To the axis, the origin point of the axis. Then you find your vector R, and you just use your mixed triple product where you have lambda dot R cross F. And we've already seen the order of appearance. Lambda first, the R second, the F third. You use your determinant calculation. You find a magnitude. Look at that, it's not bold, right? Even here, it's not a bold for vectors. So in other words, you can also easily find your M about OL by the vector R2 cross F2 if you are looking at this case, for example. So by resolving the force F into components parallel to the axis OL and in a plane perpendicular to the axis, you can show that the moment MOL of F about OL measures the tendency of F to rotate the rigid body about the axis. So the orientation is very important. Number one, you've got the axis of interest, which is OL, and you immediately come up with its directional vector. Then you've got some plane. So this plane is just defining part of the rigid body at which we have the position where the force is acting. Then you can find the location of the position at which the force is acting. This vector position is from the origin of the axis, so it's for reference purposes. So in other words, with that setup, you can now relate the vectors according to figure 3.24. So there, the moment of a force about an axis or line L can be found by evaluating the mixed triple product at a point B. So this time we no longer have the origin, so you will use the previous principle. In this case, then our moment about the axis BL will be lambda multiplied by the moment about B. What is lambda? It's the directional vector of the what? Of the axis from B to L. What is the R, which is the distance at which the force is what is acting about some reference point on the axis. So that will be your MBL. So it will be equal to lambda cross lambda dot RA cross F, and then you can use your matrix method and find the moment about that axis. If you want to think about another axis, CL, right? So this is the same thing. This is the same axis, CL. So you can also use equation. I think the should be 3.45 if I missed the number there. Okay, so there's an example here to find the moment about an axis. A farmer uses cables and winch pullers, B and E, to plumb one side of a small barn. If it is known that the sum of the moments about the axis of the forces exerted by the cables on the barn at points A and D is equal to 4728 foot-pounds, determine the magnitude of TDE when TAB is equal to 255 lb pounds. So I still wonder why we call them foot-pounds when they're written pound-foot. Isn't we write our moments as Newton meters. We don't say meter Newton. So it's very interesting. Very interesting. It's called convention. Okay, so what do we want to find? We want to determine the magnitude of this force TDE when TAB is given. So the first case is that there are moments that are about some axis, which is the x-axis. All the moments that we're thinking of are about the x-axis. So the sum of the moments is given as this value. The sum of the moments has been given as those values. So what forces are acting to generate that moment? We obviously have on this, I will not draw the free body diagram for the sake of time. So we've got some point A at which this farmer was using the winch pulley to what? To tension. So he wants to tension so that this barn is what is plumbed. So we can call that tension from A to what? To C. Then we've got some other tension that is also generated there. That would be our tension from D to F. Right, so these are vectors. So all these tensions, as you can see, it makes sense, right? If we are pulling in this direction, it's got a sense of that direction. It's obviously going to attempt to balance this building by rotating the building about the x-axis. The x-axis is what is running along that line. So if we want to find the total moment, it's obvious we need to find the moment due to this force TAC about the x-axis. We need to find the moment due to this force TDF about the about the x-axis. The x-axis is it's an axis. So what we would need to do is to add the two moments. So let's just say the moment is what? Is force times distance, isn't it? So there must be a TAC and its projection at right angles. So if we had a right angle there, we can actually make life easy for ourselves. TAC in the this is our X, our Y, so this is our Z direction. So TAC in the Z, right, is going to multiply the vertical distance, this distance. So that would be what? That would be let's just call it D1. Right, it's 12 feet. So D1. That's the moment, right? About the axis, x-axis. It's simply the force times the distance, right? Plus TDF. DF is multiplying by, remember I'm just writing it in magnitude form because we're looking at a moment about an axis. TDF is also, it also has some projection in the z-axis, right? So it means that we can easily use that projection TDF in the z and then multiply by the distance. This time it's 14 feet. So let's call it D2. So that would be D2. Okay, so as far as the D's are concerned, you already know those. So how do you get your TAC in the Z? How do you get your TAC in the Z? So it means we need to find the projection of this force TAC onto the Z-axis. How do we do that? You still remember your definition of the projection of a force onto an axis. Projection of a force onto an axis. Where is it? Where is it? Where is it? Where are you? Where are you, my friend? Yes, there we are. So if we want to project, right, if we want to project any force onto any axis, we just use the what? The dot product, P dot the directional vector of that axis. Fortunately, in this case, we are dealing with the Z-axis. So it's obviously the what? The directional vector, in this case, is what? It's the K, isn't it? Because it's in the K direction. So this is just the K dot the what? The force. And that's our TAC. The force is TAC, and we need to find this directional vector. We can just say AC in that direction. So that's our dot product. And then plus, sorry, this will multiply a what? Okay, we're just looking at TAC, so I don't need to put that. And then TDF in the Z is the same. It's just our K still in the Z. And then dot the TDF in the direction DF. So your task is to use yesterday's principles to find the directional vector, the magnitudes. One of them is known, the other is not. Okay, it's actually AB, sorry. So this, you can use B there, and then you can use E there. So if you find the magnitudes, and we know that if we add these up, these are numbers. One of these is a number. This is known. So the unknown is simply that DE. So you have one unknown, which is inside here, which you will end up extracting from the equation. So basically, that's how you would find the moment that is, the tension that is not known, the magnitude of the tension that is not known. This summarizes chapter 3.1 and 3.2. So in our live lecture, we may not be able to cover all the calculations because of time. So all the guides are in this lecture. So what's important is for us to now make use of the problems that are on the practice tests. Practice test 2 is open, so you can now wipe your hands and say you've got the theory, sit on a clean desk and calculate to figure out how you can find the moment about a point and the moment about an axis. The point can be an origin or any point relative to the origin or any point that is not relative to the point origin, origin, right? And then the second one is to find the moment about an axis. So it can be one of the x, y, or z axis, or it can be any line. So if it's any line, remember, just find its directional vector. Look for the lambda. When you find the lambda, you're good. So basically that's it for this lecture. I hope that you will make use of these principles. And the idea is practice. So if you work out at least 3 problems, let's say 3 problems, 3 statics problems per day, keep the failure rate away. Yes, okay, so that's it for today, you guys. I wish you the best and have fun with this module. Okay, all the best. Signing out.